All right, hello everybody. I hope you all been doing great. Today we're gonna have a really fun lecture by Dr. Steve Abrams. He is a doctor at Dell in pediatrics. He is also has an appointment in BME as well. You know, I really enjoy having him come talk to you guys because he talks about how, the engineering and medicine worlds kind of mix. And so I'm just going to let him go from there. You guys have always been good about participating and using chat to ask questions. He would definitely welcome your interruptions and questions. So anytime you have questions, comments, put them to chat and we can get to those as well.
All right. Well, thank you. I think the show, it's in my ballpark now. This is, for us old folks, it's hard enough to adapt to new technology, and this is an extremely new approach to giving lectures. So I'm trying to do my best, and I'm certainly in the real world, you'd be interrupting me and asking questions about this stuff. So do so. This is not, again, designed for you to be taking notes, and this is designed for you to think a little bit about how medicine and engineering interact with each other. It kind of has a little bend towards those who are interested in a career in medicine, but it's not entirely designed for that purpose. So what we're going to do is go through a little bit about my career pathway, a little bit who I am and how I got to where I am now, and then kind of go through some specific examples. So career pathway, as an MIT engineer, chemical engineering biology major. The oil bust occurred in the late 1970s, and after having a fascinating interest in a career as a biomedical engineer, chemical engineer, biomedical engineer, that came to an end. So I needed to find something else to do with my life. So I went to medical school, graduated from the Ohio State University in 1982, did a residency in pediatrics, did a fellowship in neonatology, did another fellowship in nutrition, did another fellowship at the NIH in mass spectrometry. You see there at a time when it was a really exciting thing to do. So after having done 3 fellowships and a residency, I decided to finally get a job to support the family and to move on in life, and moved to Baylor College of Medicine, where I'd done my fellowship and stayed there as faculty for 25 years. In 2015, I came to Austin and as department chair in the Department of Pediatrics, which was just being founded at the time. Stayed in that role for 3 years, and now I'm involved in coordinating and doing research at Dell Med School. And I continue to practice medicine. I am a clinically practicing neonatologist, and will be in the NICU over Christmas again this year for the 39th consecutive year in the NICU over Christmas. So a little bit about pediatrics, which is my focus. And if I was in person, I'd be telling you and I'm looking you all right in the eye and telling you I don't care about adults. Okay, that's a fundamental operating basis for this discussion. We care about children. Okay, there's plenty of other people that care about adults. I understand that adults are important, I guess, but I care about pediatrics. And I care about how pediatrics and the field of pediatrics interacts with engineering. So we're going to talk a little bit about an example of getting food to babies and how to weigh and measure babies and things of that sort. A little bit about the mass spectrometry work I did for many years related to mineral absorption. A little bit about obesity, a little bit about global health. I'm going to talk to you a little bit about my perceptions of technological fails unique to the pediatric neonatal critical care system. And then finish with a couple of slides and a little discussion of COVID-19 and food systems. So you thought that this might be the one time that you'd get away from hearing about coronavirus, but it's not. Because in fact, there are lots of issues that relate to the things that are of interest to all of us in terms of food systems and coronavirus that I think are relevant. So let's start to talk about an example, one that I worked on when I was at Baylor with the biomedical engineering department at the time at Rice University, and where I was at the time. And one of the things that we had a problem with in neonatology and still have a problem with is that when we feed babies, We like to feed them their mother's milk or donated mother's milk called donor milk. And the problem is that donor milk has the fat that separates out, or mother's milk does. And that's because the lipid system in milk is such that milk separates out. And that means that the fat rises and stays behind. Okay, so what happens is that when you feed a baby with a tube, which is how we feed premature babies, you put the tube into the stomach, you run the milk into the tube, and the fat stays behind and never makes it into the baby's stomach, or a significant portion of it doesn't make it into stomach and gets caught behind in the feeding mechanism. And that amount can be as much as about a third of the fat. So 30–40% of the fat gets left behind if you do it that way. And if you just push the food in, called infusion via gravity, you have very small losses. But our preterm babies don't tolerate that. They need the food to go in largely continuously because their stomachs are so small, and they lose their fat and they don't grow. Okay. So we worked as a senior design project with trying to figure out how we could mix the food. How can we mix the food in a way that the fat would not separate? So again, imagine, and I'm not there in person, so I can't quite describe this as well as I'd like, but imagine that you have a pump, and that pump is pushing food continuously into a baby's stomach, and it's pushing it through a tube. What happens is that the fat all stays behind in the bag and in the tube that it's going into. How can we continuously mix the food so that the fat does not separate behind? That's an engineering question. Okay, so here we have a clinical question. How do we make babies grow who are sick and premature? And we have an engineering question. How do we make a bag that works in that circumstance? So what we did is we got our students together, and literally what they did was they came up with this little device that not very well shown here, but basically the idea is that they put in a motorized bag. See, so this is the bag here, okay, that's got the food in it. And then what you do is you literally invert it as the food's going in, up and down, which is a way of shaking it, and also continually rotate it at the same time. So that at the same time that the food is going in, the food is being mixed so that the fat does not separate. And in fact, this worked. Without going through the details, we published the details multiple times. We were able to markedly decrease the amount of fat losses by using these different circulating devices. We use two different approaches. One is inversion, turning it up and down, and the other is circulating the milk while it was being delivered. And that combination of those two effects completely got rid of the 40 to 50% fat loss that occurs. Okay, so that's an engineering solution. So the problem was, and you needed to do both. So fat delivery was decreased by 40% after continuous feeds. Combining inversion and circulation loop had essentially completely got rid of that effect. But here's the problem. An engineering solution is only as good as your ability to implement it. So the problem that we had is that the number of premature babies in the United States who receive their fat this way, who get fed this way, is maybe 15 to 20,000 babies a year. That seems like a lot, but it's not. When you try to commercialize this sort of thing, we ran into a lot of trouble. Nobody wanted to commercialize it because there wasn't enough money in it to get through the commercialization and the patenting process. And as such, it really never completely took off. But what did take off are that the ideas behind what we did, that is the need to continuously turn the milk and to shake the milk, did take off. And a variety of bedside techniques are now used to continually move the milk around in different ways, whether it's a nurse just shaking it periodically, as whether or not we have it hanging upside down and flipping it around on a regular basis every few minutes, or different techniques that are being used to try to get the milk to mix better. Ultimately, I think a mechanical approach is best, but that hasn't taken off more for financial reasons than anything else. But the idea was a good one. The idea was that we could take a clinical problem known at the bedside for which people did not think that there was a engineering solution and actually engineer that type of a solution. And something that's not a device that we inserted into a body, for example. Now, I'm going to change topics a little bit, and I talk quickly, and I know that, but I got a lot to cover, and I want to take your questions and talk to you about the problem of starvation, malnutrition worldwide. We're going to come back to this a couple times, because what I do for a living is I'm chair of the Committee on Nutrition of the American Academy of Pediatrics. And one of the major things I've done for over 20 years is travel around the world dealing with the problem of malnourished children. Okay, the problem of childhood malnutrition is a severe one. Stunting means that they're short for their age, and 230 million children are stunted. Being malnourished as a small child, as a toddler, as an infant, is associated with a lifetime of problems developmentally and other consequences. It'd be nice to say that the world is getting to be a better place and that malnutrition is going away. It's not. There are some parts of the world where it's getting better. There's some parts in the world where it's getting worse. And coronavirus on a worldwide basis has been a disaster for childhood malnutrition in terms of massive increases already occurring in childhood malnutrition. So you say, that's fine. That's awful. What's that got to do with engineering? These are political. That's a political question. It's not. It's also an engineering question. So again, first we have to understand the scope. Nearly 1 billion people around the world are hungry. 3 million children die each year from maternal and childhood malnutrition. This is one of the major health problems that faces our globe. So for decades, I thought about this in terms of an engineering solution. And the engineering issue was, if part of the problem is not just the total amount of food, but the quality of the food that children get. The children much of the malnutrition is what we call micronutrient malnutrition. Micronutrients are things like iron, zinc, calcium, and vitamins that they're lacking. Macronutrient malnutrition is not enough calories, fat, protein. But micronutrient malnutrition is more common than micronutrient malnutrition. And the macronutrient malnutrition. And micronutrient malnutrition actually causes much of the pathology, much of the death, much of the developmental problems that occur. So what I did was I developed the techniques with people at the NIH and elsewhere to use stable isotopes to assess interventions. So the idea is that stable isotopes, as you know, are non-radioactive forms of minerals, using an example of minerals. So for example, iron has 4 different isotopic forms. 2 of them are relatively minor in frequency, that is 57 and 58 iron. They can be given as tracers, and then their enrichment in blood or in other tissues can be looked at as evidence of nutrient absorption. Ultimately, the goal is to identify the best solutions to micronutrient nutrition and to evaluate whether or not the solutions that we come up with are effective. So the technique that's used in these studies is something called the dual tracer method. It's a mathematical method in which one gives 2 isotopes of interest. And I'm going to use calcium as an example here, not iron. So we give 1 isotope of calcium orally, and calcium has 6 isotopes. A couple of them are very rare in abundance. So for example, 44 calcium is a natural abundance of 2%, and 42 calcium has a natural abundance of 0.6%. If we give 1 orally, so for example, 44 calcium orally, and 1 intravenously, the relative amounts of these that occur in the blood or ultimately get excreted in the urine are a reflection of the amount that got absorbed And one can use turnover kinetics to determine the rate at which they disappear into or out of tissue, in this case for calcium being bone. So this tells us whether, if we give calcium or other minerals like zinc, if it got absorbed into the body and where it gets deposited. So this is called the dual tracer method. It can be used for a lot of different things and relies on the ability to give non-radioactive tracers to small children, pregnant women, and the like, to measure without collecting stool whether or not it got into the body and whether or not it got into the tissues of interest. Analytical methods are mass spectrometry. Minerals are analyzed on either ICP mass spectrometry or thermal ionization, TIMS mass spectrometry, in some cases by neutron activation. These mass spectrometers are not cheap. This is a thermal ionization mass spectrometer. It's a version of something called a small version of something called a calutron, which originally was used to separate uranium for use in the development of the initial nuclear weaponry during World War II and thereafter. This is a very tiny version of it, but basically what you do is you heat up a mineral inside the source here to a very high temperature. You run it through a magnetic field. The ions are separated and then counted, and the relative isotopic ratios are measured. So you can determine whether or not the isotopes that you gave, and then you obtained your sample of blood or urine, enrich them. ICP operates very similarly. So let me give you an example of this. So in Mexico, a number of years ago, this is about going back close to 20 years ago, they had a program in which they were giving iron and zinc enriched food to toddlers via a program that was called Progresa. It was a national program that was designed to resolve a severe problem with anemia in parts of Mexico. And they did something interesting. They gave them this food that had they gave it out free. They literally spent a couple $2 billion on this program. And a year after they started it, they went and they assessed what happened. And they discovered that they'd spent something like $2 billion and had absolutely no effect whatsoever on the health of the children, their iron status or anything else. So they came to me and said, what went wrong? They said, well, the iron that you're giving them probably can't be absorbed. And sure enough, that's exactly what happened. We went and we spent about 100th of that amount of money to actually measure what happened. And we discovered that the iron absorption in these kids varied based on the iron source. And we ended up coming up with different levels of iron absorption based on which iron source that they use. And that to this day is the basis for almost all of the iron fortification programs that are used in Latin America. We wanted to expand this idea and ask the question, can we develop a beverage that would have lots of iron and zinc in it, that would be highly absorbed, and that would be helpful for school kids, a little bit older kids that could drink a beverage? And we were approached by the CocaCola company. The Coca-Cola company was interested in this because the Coca-Cola company has some interest in trying to suggest that they're not all selling bad food, but that they can sell good food. Coca-Cola is the largest employer in much of Africa. Coca-Cola has a vested interest in not being seen as simply as a junk food company. You can decide for yourself if you agree with that, but they have a vested interest in that. And they produced this beverage. And the question was, did the beverage work? Did the iron and zinc get absorbed? So we went to a couple of different places and we tested it with stable isotopes. One of them was Lima, Peru. And we actually assessed iron absorption when it was given with or without a meal. And without going through the details, because they're not so important here, what we found is, in fact, there was a slight benefit to giving it without a meal compared to with a meal, but both ways it was well absorbed. And the product, in fact, was quite effective in getting rid of much of their iron deficiency. What happened next? Well, this is what's interesting. And it's just as I told you about the mixing problem with fat and how we came up with a technological solution that wasn't used. Here again is a technological solution that had only limited success. And the reason was the marketplace. The technology was never the issue. The beverage worked. But the cost of the beverage, like the cost of many of these fortification programs, was too high. And in fact, most people couldn't afford it. Nonetheless, food fortification of this sort is used, beverage fortification is used, and the principles behind assessing outcomes, including bioavailability, remained. One thing that did change is I started getting involved with the business schools and started asking the question, if I come up with a technological solution, is it financially viable? Because if it isn't, then it's not a good solution. All right, those are a couple of examples. Now I'm going to be a little more broad-based and talk about specifically about challenges and opportunities as I see them in pediatrics. If anybody has any questions up to this point of these examples, now would be a good time to either speak up, which you're welcome to do directly, or put them in chat, whichever works for you. Anybody have anything before I go on?
You know, I told Dr. Abrams, you guys were very talkative in chat and nobody has had a single message today. So I think you're making him feel bad.
Okay. You'll have more chances at this, but it's kind of hard to get your mind. Some of these ideas are really different, and things that you haven't thought about because you're new to this field. And I've been doing this for 40 years, trying to figure out how to make technological solutions work. Let me go through some of the let's see. Okay, try and take it all in. All right, so let's go through. Whoops. Let's go through some challenges. Now I'm going to start, and now I want you to really get your kind of your thinking hats on here. Okay. So let me give you a simple problem that's a challenge, and I want you to really think about this. If we're going to figure out whether or not a baby is growing, we need to be able to measure it, okay? Now, this sounds really simple, but it's one of the most frustratingly difficult problems that we have, especially working in lower income countries. And there's two aspects to this. There's the actual making the measurement, getting a scale that works. And number two, there's recording the data in a way in which we can make use of the information. So let me tell you how this works in the United States. In the United States, when we have a small preterm baby, we put them in an incubator, and the incubator has an electronic scale in it. And every day, what the nurses do is they weigh with the electronic scale, they weigh the baby on the bed, they lift the baby up, and the electronic scale then separates out the difference in weight between the baby on the bed or not off the bed, and the difference is the baby's weight. It's all done not electronically. It's highly accurate within 1 to 2 grams, and it takes very little effort. So what is that? And then the next thing that happens is that the nurse enters that information into a medical electronic program. The one most commonly used is called Epic. Okay. And that electronic program then, that's how I weigh my dogs. Yeah, that's basically the same approach as I use to weigh my dog too. Okay, so that works. But let's think about this in a developing country situation. First of all, you have to have an electronic scale is unheard of. Then incubators they're lucky if they have them in some place. If they do, they certainly don't have an incubator that has an electronic scale on it. Goes for $30,000 to $40,000. These countries are working on scales in the hundreds of dollars they can afford, not the $30,000 to $40,000. Okay, and second of all, they don't have in some of these places they don't even have reliable sources of electricity. So an electronic scale doesn't, I mean, they're basically measuring things like I did in high school of weights and balances, okay? So which are not very accurate and not very technologically usable. The second problem is making use of the data. So in the United States, what I would do with this situation is, again, we put the data in an electronic sheet. We look at the sheet calculates percentiles, it calculates growth rate. I can get the electronics to tell me how many grams per day the baby's growing. I can get all of this stuff done. But the problem is that they don't have any of that. All right. Now you have, I'd say this is the equivalent to flying a plane without radar. Okay, trying to make a premature baby grow without electronics way to assess growth is almost impossible. And we actually attempted multiple times to fix this problem and had absolutely no success. It's a pure engineering problem. How do you make a low cost scale? How do you apply it into an incubator? And then how do you create an electronic system to plot growth without having use of a multi-billion-dollar epic computer system? That's an example of things that has yet been solved. No one's even come close to solving that. All right. Let's take on another okay, questions about that. I saw there's some stuff in chat. Any questions about that? Let me take a look here. Okay. How do engineers not get discouraged by the limitations of cost? That's a really good question, because I think my best answer to that, we'll talk about that some more, is to be aware of the issues of cost. So the solutions that we come up with, I mean, first of all, our job is to make the solutions technologically work. Okay, a solution that's technologically crummy isn't a very good solution. That's obviously, but that's our job. But we also have to be aware of the costs involved. Now let me give you another example. It's broad. So let's talk about pediatric obesity, a big problem throughout the world. That's real. Techniques to measure body fat or lean body mass are inadequate, not easy to use. I won't go through them. They exist. Dietary data intake techniques are antiquated. So for the example of this is the way we figure out what somebody eats is we do what's called a 24-hour recall. Okay, that is, we ask them, what did you eat in the last 24 hours? Now, I don't know about you, but very few people remember what they ate in the last 24 hours or 48 hours. And even if they did remember, no small proportion of people, when asked by somebody, a dietitian, about it, won't be 100% truthful. Are you really going to mention each candy bar bite that you had, the little popcorn that you shared from your neighbor back when we had neighbors, and all that sort of stuff? So our techniques are antiquated. What would be better would be, again, visual techniques. What if you participate in a study, what if what you did is you took a picture of your plate and then that picture got translated into caloric intake by a computer program that said, oh, okay, he had mac and cheese. Mac and cheese has XYZ number of calories in it, et cetera. And that program then had in it all the major brands of foods, et cetera. That wouldn't be ideal for when you homemade your meal, when your mom made you her homemade lasagna, because it'd be a little tricky to figure out exactly what mom put into your homemade lasagna. But nonetheless, that would be a huge step better. Okay, those techniques are actively being worked on, but have not been very effective. Let's talk about another technological solution, which is, how do we convince kids that they should go, and instead of getting French fries with their hamburger, that they should get fruit slices? Well, one technique people have been trying to work on are text messages. Hey, John, about to go off to get lunch. Remember to have a piece of fruit with your lunch, kind of thing. They can be reasonably effective, but again, they are not easy technologically to make happen, be non-invasive, etc. So these are major healthcare problems that are, in fact, that have the solutions in the realm of technology. And when we get to body composition in infants and pregnancy and the like, it becomes even more important. What are some technological challenges that are unique to my field, pediatric and neonatal critical care? I'm just going to give you some examples. Delivery of tiny volumes, dead space in human areas. What do I mean by that? In a premature baby, we calculate their fluid intake to the nearest 1/10 of an ml, sometimes even not 1/100th of an ml. Okay, the technological side of this. So if I give you an antibiotic, the technological challenge of measuring out 0.164 mLs are really significant at the bedside and not something that you can just readily get past. When you translate that to global health, it's even worse, where they simply don't have the technology to deliver those. This affects everything that we do. Everything that we do is the inability to assess tiny volumes. Okay, and you can think about that. Nutrient compatibilities, patterns of vital signs. There's some evidence that the pattern of your heart rate and your respiratory rate, actually, if you're a small baby, a premature baby, affects your likelihood of having a bad developmental outcome. That's a technological challenge. In fact, it's been worked on at Del Med by some of the people in neurology. If we have a continuous recording of a baby's heart rate for 6 or 9 months, can we interpret that then with what their developmental outcome is 3 years later? These are the kind of thoughts that are out there. All right. We already talked about the money part of it. The part of the problem is it's not. Babies, children are a small portion of the healthcare world. These types of solutions are very difficult sometimes to get funded, but they're important. Global health, I've mentioned some examples. I'm going to give you a couple more examples before I move on to a few other final kind of things. Some of the things that people are really working on very hard on a global health technological basis are, I mentioned the incubator issue. We need to have incubators for Africa that do not rely on a consistent source of electricity. CPAP devices, you know what CPAP is, holds air in your mouth. Non-invasive surfactant, delivers surfactant, helps open your airway if you're a sick baby. Point of care testing. So for example, we test babies for congenital anomalies of thyroid deficiency. Trying to do that in developing countries is difficult. One of the ones that's being worked on a good bit by some couple of different groups, including one in Austin, very hard, is oxygen blending. So the story here is that if you give a small premature baby oxygen, that's good. But if you give them too much oxygen, you cause vascular damage to their eyes with a risk of blindness. It's called retinopathy of prematurity. It's one of the leading causes of blindness, along with vitamin A deficiency in the world. In order to solve that, you have to blend oxygen. That is, not just give 100% oxygen, but be able to give 30% or 40% oxygen. And adults, this doesn't matter. They just give you 100% oxygen and blast it away. But it makes a huge difference in sick babies. The problem is that this requires blender technology that's available in almost nowhere in the world outside the United States, highly industrialized countries. So literally hundreds of thousands of babies are going blind every day, every year in the world because we don't have the technology to blend oxygen properly in developing countries. Okay, these sorts of problems. You need to identify our targets. The needs of Latin America are different than the needs in Africa, are different than the needs in Asia, etc. Okay. What about next steps? And I'll stop then. Any comments I should respond to? Any questions before I go on to next steps? Everybody's trying to figure out how to weigh the dog. Okay. How is someone able to view political social issues as an engineering issue? Are there limits of social and behavioral impact of technological solutions? Sure. The most obvious example of that is GMO. Okay, genetically modified organisms. Okay, so we can take rice and we can make rice be high iron. Rice naturally is low iron. Rice is the #1 food crop in the world, but that requires GMO technology, which is highly political, and not accepted. So there's absolutely and the Gates Foundation has literally poured billions with a B into GMO technology to enhance the nutrient composition. And I'm not going to get into an argument about the safety and pros and cons of GMO. We can do that another time. but failure to appreciate the political aspects and the sociological aspects of GMO technology has sent billions of dollars down the drain. And that's the cleanest example. There's many, many more. That's the cleanest example of technology that where the technology, if it doesn't match with the public policy, fails. Oops, I'll go back and talk about this slide. Next steps. Well, if you care about this field as you go forward in life, you need to find out what the problems are at the bedside. I can't tell you, I've given you examples, but I can't tell you what the problems are. You need to go to the bedside and literally, one of the things I do sometimes is go into an intensive care unit and ask the nurses, what's your biggest headache? What's your problem hour to hour other than staffing? And one of the things that they're going to tell you is too darn many cords, for example. Okay, they're tripping over cords everywhere. Look and see how a cardiac bypass circuit works. Actually watch it work and then think to yourself with the minds that you have, what can be done to make this system work more effectively for the people using it? Okay. I always encourage people to care about what happens to children. I know that there's always a lot of interest in engineering about making a better knee or a better cardiac valve for adults. And I'm not trying to tell you that stuff's not important. Of course it is. But just because there are perhaps 50 million Americans at any given time that have a bad knee or a bad shoulder, there are maybe 50,000 people that have a tiny premature baby that needs assistance. So scale is vastly different, but that doesn't mean that you shouldn't do it. Always remember that incrementalism is good. Okay, that can be a hard idea for us sometimes. We want to design something that's all new. But if you can just figure out a way to get the electronics in an ICU so that everyone isn't tripping on cords all the time, you've made a huge difference in the care of those patients. Incrementalism matters.
Steve, there were a couple questions. One was
Sure.
about, are there any technologies to help decrease the margin of error in measuring instruments in developing countries?
A lot of people are doing that kind of stuff. The answer is, the problem is that the feedback loop is awful. That is, that the problem is when we introduce these technologies into these settings, we can introduce ventilators, we can introduce a lot of technologies, but assessing the feedback loop of assessing whether or not what we did was effective is often the lacking step. So yeah, people are trying to do that, but there's been this long history of dropping off technology into global health markets and not assessing what actually is effective. And that's the big problem, is getting the feedback loop on that.
And I think the other question is just how approaching the cost limitations of like not being able to make money on a device. Like how do you approach that?
Sure, involves getting to know what your funding sources are. The largest funding source for global health in the world right now, hands down, is the Gates Foundation. Like it or not, it's the Gates Foundation. There's lots of different organizations that are involved in trying to do this. You have to assess who they are and what the purpose is of that organization in order to give funding out, because the funding mechanisms that we have here in the United States are not the same as the funding mechanisms of global health. And it involves getting to know what those mechanisms are, getting to know who the people are and how they're interested in solutions. They tend not to be interested in theoretical research. They tend to be interested in field research. And that's okay, but you just have to become aware of that kind of universe. I've mentioned a lot of this, and I'm not going to go through it because I want to finish up the last little bit we have with some thoughts about careers. So here's just some of the global health stuff, and I think I've pretty much covered most of these in terms of issues. So should I be a physician? I also want to leave myself with a couple minutes here to talk about coronavirus. Should I be a physician and a biomedical engineer? Well, that's your decision. I asked some thoughts to think about. And one of the things that I try to do as best I'm able For those of you, and some of you on this call know this, most of you don't, I'm more than glad. It's an interesting world right now. I can't sit and meet with you in person right now, hopefully soon, but I'm glad to answer questions. Dan and others know that I've always been able to reach out. Right now, I've got a couple students working with me. I don't have particularly necessarily need for other students working on me on my research projects right now, but I'm always welcome to answer questions. Are there easier routes into medical school? Is that the goal? Always be prepared to answer why you chose this route and how you plan to use your engineering schools in medicine. I always remind people not to skip doing all the usual pre-med activities. No one's going to admit you to medical school because you're a biomedical engineer who didn't bother to shadow, didn't do community service. I encourage you to try to find both a BME mentor and, if possible, a physician mentor. Again, coronavirus has made that a little bit harder, but they're out there. If you really love engineering and want to be a physician, consider MD, PhD. And that's a talk that should be all by itself, honestly. But the MD, PhD is a primary research, not a clinical pathway. And again, sometimes there's a bunch of questions about that, and I can take one or two. I'm not an MD, PhD. I chose not to go that route. There are pros and cons to it. If you are an MD, PhD, want to go MD, PhD, engineering is one of the better routes for the PhD because you can get your PhD relatively quickly and apply it relatively quickly compared to some of the more immunological and basic science kind of things. But you have to understand that MD, PhD is a research path, primary research, not a primary clinical pathway. Remember, you only become a physician if you want to take care of sick people. Becoming an MD, whether it's an MD, PhD, or whatever, for the purpose of becoming an engineer that knows how the body works is a really, really, really bad idea. You'll regret it every day. Only become a physician for the most, with rarest of exceptions, if you wish to take care of sick people, as well as use your engineering.
So related to that, there's a question, what made you interested in pediatrics, and then how do you like working as a doctor who takes care of people versus the engineering side of things?
So first of all, I chose pediatrics because you might have guessed I care about kids a lot more than I care about adults. Always have. I always have my whole life. So, and also I felt as I developed over time, my career over time, that there are a lot fewer advocates for the rights and the needs of children, and that was therefore the place that I wished to be with my career. I enjoy both clinical care and the engineering, and I've never chosen to give up one or the other. There will be times in your career where you have to, if you're going to have a research-focused career, where you're going to have to decrease your clinical work, increase your research. There'll be times when it goes the other way around. And you just have to be flexible to that. It's not easy because being a successful researcher requires that you commit a majority of your time to research, not patient care. But I enjoy doing both and have no intent on giving up both. Pros and cons of being a physician trained in engineering. Pros, and I always say that engineers are the process people. We understand how data comes to us. We understand when data is weak. We understand error recognition. You don't know how often in a clinical basis I get told about a lab value that's abnormal, and I simply point out that the normal values are the 95th percentile of normal, and error margins and technological issues in the measurement lead to errors. And just the average physician has no concept of any of the basic concepts behind engineering thought that you are all learning, and those will be useful to you. The cons is there's less time for some of the activities. I've listened to a couple of my favorites. You've hinted at the resentment and cynicism about human failures. It can be very frustrating as an engineer to watch the human failures in medicine and say, why can't this be fixed? If this was a widget, we'd build a better widget. Why can't we build a better doctor? And obviously social isolation. Hate on the eggs. I usually, in the version of this, I typically said hate on Michigan Wolverines because I'm a Buckeye. The Michigan Wolverines suck so badly at football this year. I don't need to say that. I feel embarrassed for them, so I don't need to remind you that Ohio State is better than Michigan in football. But we can certainly hate on the Aggies and the Sooners. All right, I'm going to conclude the last what I have here, 4 or 5 minutes, and talk about hunger and food insecurity in America and COVID-19. I'm going to zip through this a little bit because I don't have too much time. Then we'll leave you time to ask questions, a couple minutes more for questions. Hunger and food insecurity are a major problem. 1 in 6 children in the United States are food insecure. One can screen for food insecurity with a simple 2-question screening questionnaire. It's approved by the American Academy of Pediatrics. Within the last 12 months, we worried about whether or not our food would run out, or we got might buy more, or our food didn't last. That's food insecurity. In terms of COVID-19 and food systems, food insecurity is already common. Usually about 15 to 20% of a population is food insecure. That includes college students. At UT Austin, the rate of food insecurity has been documented to be 20 to 25% of our college students. That's you. Since COVID-19 has taken over our existence, the rate of food insecurity in the city of Austin has increased to 40 to 60% among low-income families, especially Hispanic families, especially those who do not have English as a primary language. The rates trend with job losses and infection rates. We've published some of this stuff already. The interaction of infection and malnutrition are closely associated with worse medical outcomes, which is a fancy way of saying if you're malnourished, if you're hungry, and then you get coronavirus or another virus, you're going to be worse off. What can engineers do about this? So here's just a couple of ideas I came up with as the kind of the last topic. Families can't get the food because they don't have transportation. Okay, this is a complex problem that requires understanding how we provide food to low-income families. So, for example, the WIC program, the SNAP program, food stamps, all rely on technology. They rely on cards that have to be recharged. This whole technological system fell apart during coronavirus. The whole system has fallen apart. And that's long beyond what I can explain to you in the next 2 minutes. But suffice it that the technology has failed us in order to figure out how to get food to people, okay, in all sorts of different ways. The food delivery systems we have are inadequate to deal with the pandemic, resources stretched, inadequate shared. You would think that there'd be an electronic system by which families that need could log in and find out what food banks are open when they could get food. Nothing of the sort exists. We have a complete and total collapse of electronic systems and technological solutions by which food can be gotten to people who are hungry. Information lacking in multiple languages. A lot of people don't have access to the internet. The assessment tools we have are not adapted to internet use. So WIC, which feeds babies, measures babies to make sure they're growing okay. You can only do that in person. Attempts to use home scales, electronically transfer information about height, weight, and the like have all failed and not been implemented. There's a lot of misinformation out there about food, about vaccines, about vitamins, all sorts of things. Misinformation campaigns run rampant through the internet. We need a solution to how to deal with misinformation. And then there's, I mentioned, biotechnology of food itself, which has become a challenge in the coronavirus environment. So there's lots of things that can be done, even as we look at a problem like coronavirus, that require engineering solutions. Remember, nobody's perfect, but just because you can't solve a problem doesn't mean that you're free to attempt to do the best you can to deal with it.